column stress is there. That is limitation of Euler's column theory. That will discuss. After that, I will move on to the second part of the model. Okay, that is deflection of the beam. Okay, we write the headline as limitation of Euler's theory. Okay, based on Euler's theory, we have derived the equations for buckling load or crippling load of the column, correct? So there is some limitation column theory that we will see, and I will move on to the second part. Write the headline as limitation of Euler's column theory. Limitation of Euler's column theory. So in case of columns and struts or in fifth model, there is only two theory questions. One is assumptions made in Euler's column theory, and one more limitations of this Euler's column theory. Okay, so it is important for the point of your examination. Okay, now let us see what is the limitation of this Euler's column theory. Okay, so before we going to discuss limitation of let me explain two things. One is buckling stress, or crippling stress. Okay, buckling stress or the crippling stress. One is okay. So you need to first understand what is the difference between this buckling stress and the crushing stress. Okay, buckling stress means if you take a column, so let us assume centroidal axis as, so this is the centroidal axis of the column. If the axial force acting on the column, okay, is not if the compressive force acting on the column is not situated at the centroidal axis of the column, what will happen? It will cause bending of the column, correct? It will cause bending of the column like this. Okay, so buckling stress or the crippling stress is the stress at which the column fails by buckling or bending. Okay, the buckling stress or the crippling stress is the stress at which the column fails by buckling or bending, is called as buckling stress. Similarly, the crushing stress means instead of applying this force, concentrated force P, at any other point, if you apply exactly at the centroid of the column, okay, if you apply the same force exactly at the centroid of the column, then failure of the column when the force is applied exactly through the centroid of the column. Okay, the stress with which the column failed by applying force at the centroid of the column is called as crushing stress. Okay, now if we compare this crippling stress and crushing stress, or if we compare buckling stress and the crushing stress, so which will be more? Which one will be more for the column? Crushing stress will be more, or buckling stress will be more? Crushing stress will be more, because see, if you apply force exactly at the center of the column, okay, it will carry more force. It will not undergo any bending or buckling. Okay, it will undergo just bulging like this. Correct? If you apply the force exactly at the center of the column. Okay, so it will undergo just bulging and it will fail. But if you apply any other point other than the centroid, it will undergo bending, then it will fail. So when you compare the bending stress or buckling stress to that of crushing stress, the crushing stress of the column will be more. Okay, stress with which the column fails when you apply the force centrally will be more when you compare the stress when you apply the force any other point other than centroid of the column. Okay, so it's a common sense, correct? If you apply centrally, it will carry more load. Okay, it will induce the more resistance to the force. That is nothing but stress only, correct? That is nothing but stress only. More stress will be induced for centric load and buckling stress will be less. Okay, with a small amount of force, okay, with a small magnitude of the force only, the column will fail. That is buckling stress. Okay, therefore, first you understand that the crushing stress for the column will be always more than the buckling stress. Okay, crushing stress of the column will be always more than buckling stress. Okay, based on this concept, so we have a formula for standard formula for this crippling stress FCR. We know that. I'll write that formula. For crippling stress, we have a standard formula that is given by pi square E divided by L E by K whole square. Okay, where L E is there, no, that is the effective length of the column. It depends on end condition of the column. If you take the columns with both ends hinged, for a column with both ends hinged, what will happen? What will happen? The effective length LE will be equal to L only. Whatever the length of the column is there, no, that will be the effective length. Okay, therefore the crippling stress FCR becomes pi square E divided by L by K whole square. This L by K is there, no? This L by K. This L by K is called as slenderness ratio, where this L by K is called as slenderness ratio. Okay, where L is the effective length of the column, K is stiffness of the column. Okay, K is stiffness of the column. Okay, so FCR is equal to pi square E divided by L by K whole square. Okay, now based on this equation, as the denominator increases, FCR value decreases. When the denominator decreases, FCR value, that is crippling stress value, will increases. So this slenderness ratio and crippling stress are inversely proportional to each other. Correct? This crippling stress or buckling stress is inversely proportional to the slenderness ratio. When the slenderness ratio goes on decreases, crippling stress goes on increases. Okay, crippling stress goes on increases. Now, as this L by K goes on decreases, this crippling stress goes on increases. As I said, as we all know, the both are inversely proportional. But this column will have standard value of FC, that is crushing strength value. Crushing strength value. Okay, a crushing stress value. Okay, the column will have standard value of FC, that is crushing strength. Now, as I said, as slenderness ratio L by K goes on decreases, FCR will increases. Okay, but at some particular value of this L by K, at some particular value of this slenderness ratio, this value of FCR becomes greater than FC. Okay, at some particular value of slenderness ratio, this value of FCR, that is crippling stress value, becomes greater than crushing stress, which is practically not applicable. Okay, which is practically not applicable or not accepted. Okay, this is what the limitation of the Euler's theory. Okay, this is what the limitation of the Euler's theory. For example, if I give you an example, okay, if I give you an example, if you take a particular column, okay, with some crushing stress FC value as 3 around 30 Newton per meter square plus E. Okay, it's a basic property. 2.1 into 10 power 5 Newton per mm square. Okay, to find value of slenderness ratio at which the crippling stress becomes more than, what you have to do is you have to equate both crippling stress and the crushing stress. Okay, let be equal to crushing stress. Okay, we have the formula FCK area formula just now I have done, that is pi square E square equal to 330. That is here why we have equated and Young's modulus 2.1 into 10 power 5 whole divided by L by K whole square is equal to 330. Okay. If you find L by K value, L by K whole square, if you take this to the RHS of the equation, it becomes L by K whole square is equal to pi square into 2.1 into 10 pi divided by 330. By this you will get a value, that is slenderness ratio value. You just calculate and tell me the answer. If you find L by K value, L by K whole square is equal to, if you find this is 62. Taking square numbers divided by as 79.2, which is approximately 80. Okay. Now, by this, what we can understand is up to standard value L 80, this value 80, then the spring stress becomes the crossing stress. That is the meaning. When value, okay, slenderness ratio becomes equal to 80, then at that condition, crippling stress becomes equal to crossing stress. But practically, this stress will be less than crossing stress. Crossing stress. If L by K, if you further reduce, okay, if you further reduce the value of this L by K, what will happen? What will happen? This crippling stress becomes more than crossing stress, which is not applicable for, because when you take crossing stress is more compared to crippling stress for a particular column. Okay. Therefore, when this slenderness rate becomes less than 80, A goes less than 80, crippling stress becomes more than crossing stress, which is practically not applicable. This is only the limitation of Euler's theory. If I write a graph, okay, if I write a graph, so when L by this slenderness ratio in this and on y axis, and for any column, this crossing stress value will be constant. Okay, let us take crossing stress value is okay. This much is the. Then initially L by K is higher. L by K is higher. Lower. This crossing stress and inversely proportional. L by K is smaller. FCR will be higher. When L goes on increases, FCR goes on decreases. So the nature of curve, what we get is, this is not the nature of curve we get from that equation. As I said, central acceleration FCR inversely proportional. At when the L by K value is smaller, then higher will be the FCR value. When L by K goes on increases, FCR value goes on decreases. So here you can see when L by K reaches some particular value, this FCR becomes equal to FC. That is becomes equal to the crossing stress. Okay, when you further increase L by K, FCR becomes less than FC, which is practically not applicable, which is practically not accepted. Okay, which is not. Therefore, we can accept the Euler's column theory up to here, friends. Up to here we can accept. But beyond some particular value of slenderness ratio, FCR becomes this value of FCR becomes more than the FC value. Value of FCR becomes value, then in that case this Euler's column theory is not applicable. You can see that up to here this FCR value is less than FC. Up to here we can Euler's column L by K reduces beyond some value. Then here if you take this point, this FCR is here, it is greater than LC, which is practically accepted. So we cannot accept. This portion is not accepted. Only we can accept this much. So the limitation of inverse column where ratio of the column reduces beyond some value, then Euler's column theory is not applicable. That is only the limitation. So if a question is asked in your theory examination, you have to write this graph and you have to give some explanation. If possible, if you give one example, then it will be better. Okay. So this completes the limitation of the Euler's. The model is over. This constructs. We will move to the second part of the model, that is deflection of beams. Write the headline as deflection of beams. Part deflection of beams. So you will have questions from both the model, either from deflection of the beams and questions from column sets. So problems of this deflection of beams are very easy, students. You need to do some integration. Okay, by integration method, you will find some equations for deflection of the with different solutions and loading conditions. With different conditions and different loading conditions. Okay, so in this model, you are going to study how to find the deflection of a beam to a particular type of force provided with a particular type of surface. Okay, how to find the deflection of a beam when it is specific load and support. Here we will get different cases for beam. We have studied how to draw bending moment diagram and so beam, like cantilever beam, simply supported beam, different types of loads like uniformly distributed load, point load, uniformly varying load. You are going to derive the deflection of beam when it is related to some kind of load and when it is with support. Okay. Here, the same thing. If you understand one particular problem properly, okay, we can apply the same principle to solve all other problems. The principle behind solving the problem is same only, but the end conditions or support conditions and loading conditions will vary. Okay, and accordingly you need to do the calculation. That's it. But procedure behind solving is same only. Okay. Now what we will do? We will take one particular case, that is simply supported beam loaded at the center of the span. For that, be the equation for deflection. at the center. Okay. Now what I will do? You read the headline first. Headline. First one, first derivation. Okay. Derivation. Deflection. Of simply supported beam a point load carrying a point load at the center. At the center. Okay. And the method we follow for finding the equation of deflection is called as the method. Okay, you write double integration method. Double integration method. Okay, and method what we follow for finding the equation, no? That is double integration method. The questions they will ask like that only. Find the equation for deflection of a simply supported beam by double integration method. Okay. Now we'll take simply supported beam. It's a simply supported beam carrying a point load. Okay, we'll draw the figure for the same. I'll write figure of a simply supported. Now simply supported beam is a simply supported beam. On the ends of the column, it is provided with both ends of the beam. The simple supports have been provided. Okay. Simple supports have been provided, and it is said that there is a point load at the center. Okay, we will apply a point load at the center. We will apply point load at the center. So on either side, L by 2 and L by 2. Okay. Now if you write a deflected shape of the beam, okay, So this is what the deflected shape of the beam. Now our aim is to find equation for deflection of the beam when it is subjected to concentrated load at the center. Okay, means we have to find the expression for this YC. If I take this column, this point as A, this point as B, this point as C, we have to find the expression for YC, deflection at point C. Okay, where we have the maximum deflection in the beam, at center of the beam we will have maximum deflection, that is at point C we will have maximum deflection of the beam. So we will find expression for that YC. Okay, we will find expression for YC. That is what the main aim in this particular problem. Okay, now we will consider a section. We'll consider a section at a distance x from support A. At a distance x from support A. I will consider a section XX at a distance x from support A. Okay, for deriving the equation. Now first step is to find the reactions at the supports. Okay, if you find reactions at the support on both sides, what reaction will get, students? If you find reaction at the support, see here you can see the beam is simply supported beam subjected to a point load at the center of the span. Point load at the center of the span. So if you find the support reactions, you will get W by U as reaction at the support. Okay. See here the loading is symmetrical. Whatever the load acting on the beam, it will be equally distributed to both the supports. Okay, in that way the support reactions will be total load acting on the beam divided by 2. That's it, W by 2. Or else if you want, you can find by applying equilibrium conditions. Okay, if you want, you can find by applying equilibrium conditions. Even if you find it, you will get answers. That is W by 2 only, you will get it. Okay. Now the reaction will be, reaction at the support will be total load acting by 2. Total W only divided by 2. So the total load acting on the beam will be equally distributed to both the supports. So W by 2 on both the sides is the reaction at the support. Okay. Right. If we should write parallelly. Reaction. So as some introduction, consider a simply supported beam. Consider a simply supported beam subjected to point W at center of the. Now for derivation, also consider a section XX at a distance x from A. Distance exponent support A. Okay. Now the reactions at the supports will be equal to, therefore reactions at the supports is equal to RA is equal to RV is equal to total load W divided by 2. That's it, W by 2. The same thing I have written in the figure already. Now, in the next step, you need to find bending moment at section X. XX. Okay, bending moment at XX is equal. Bending moment at XX is equal to M is equal to, I'll call bending moment as M. M is equal to, what is the bending moment at XX? It will be W by 2 into X. Correct? W by 2 into X. Force is W by 2. Perpendicular distance is X. So it is M is equal to Wx divided by 2. Okay? But we know that for bending moment, we have a standard equation, that is EI into d square y by dx square. Okay? This equation we have utilized in case of derivation buckling load of the column with different support conditions. Correct? We know that M is equal to EI into d square y by dx. Both these two equations we can write as EI into d square y by dx square is equal to Wx divided by 2. Okay. Now we can see what is the method we are following for this derivation. We are following double integration method. Correct? We are following double integration method. Now we have obtained the equation for moment by taking moment at section X, that is M is equal to Wx by 2, and we also had a standard equation for M, that is EI into d square. We equate we can equate the branches of equations by that we get EI into d square y by dx square is equal to Wx by 2. So the we are following we equation X. And we know equation for deflection. Okay, what do you do? You have to integrate this equation twice with respect to X. Okay. Now integrate. So step writing the reactions in the moment equation step. Okay. Now step 2 is integrate step 1 is over here first we and we determine when the section is considered the standard deviation for moment. We so this is the first steps. Okay, I move on to the step 2. Step 2. Step 2 is you need to integrate this above equation twice. Okay, integrate above equation to integrate above equation with respect to integrate the equation with respect to EI d square y by dx square is will be dy by dx is equal to w by 2 is the constant towards integration x. It is x square by 2, correct? Plus C1. Okay. Following the session, Bharat, Moksha, Abhishek, Krishna, everyone
Yes,
can
sir.
reply.
Yes, sir.
Okay. Okay. Now, I have integrated the above equation with respect to x. Integration of square by d square x is constant taken outside, and the integration is x square by 2 plus c1. See where what is c1? C1 is the integration constant which we have to determine by applying boundary conditions, like similar to the columns and struts. Okay. Now, boundary condition. Boundary condition. Now you look into the beam and apply a suitable boundary. You will get the C1. One more thing you remember, it's dy by dx. Okay, dy by dx represents slope of this depicted shape of the curve. Okay, this dy by dx represents slope of this depicted shape of the curve. Okay, if you take slope center, if you get to the depicted shape of the beam, here you can see that slope is 0. At this point, slope is 0. The angle is 0. The same condition we will apply here. What is that? At x equal to L by 2, x equal to slope dy by dx equal to 0. That boundary condition, right? And let it, we will get the value of constant C1. Understood? At the center of the beam, there is no slope. There is equal to 0. Slope is equal to 0. Therefore, at x L by at x equal to L by 2, let the boundary condition. There is nothing in remembering. Okay, you need not remember. Just by observing the figure, you can write the boundary condition, students. At x equal to L by 2, here at x equal to L by 2, the slope dy by dx is equal to 0. Okay, slope dy by dx equal to 0. Therefore, therefore, you call this as equation number 1. Equation 1 becomes dy by dx equal to 0, correct? So this LHS becomes 0. LHS becomes equal to 0 is equal to W by 2 This 2 into 2 is 4, no? I will write 4 instead of 2 there. W by 4 into x square is there. X is what? It is L by 2. L by 2 square is there, whole square, plus C1. Okay. So it becomes 0 is equal to WL square divided by 2 square is 4. 4 into 4, 16. C1. Therefore, C1 is equal to minus WL square by 16. By this we got the value of integration constant. Therefore, equation 1 becomes, if you substitute the value of C1 in equation 1, substitute above value above value in equation 1 you get EI into dy by dx, EI into dy by dx is equal to W by 4 x square or W x square by 4. C1 is nothing but minus WL square by 16. As WL square by 16. Okay, what I have done is I have substituted the value of constant C1 is equal to minus WL square by 16 in this equation 1. Okay, we got this as final equation. Okay. Now, as I said, we have to integrate twice. Okay, when we have integrated for the first time, we got this equation. Okay, that is W by 2 into x square by 2 plus C1. Then we determined the value of C1 by using boundary condition. We have substituted the value of C1 here in this equation. This is what the equation after first integration. As I said, we have to integrate twice. Okay, double integration method. This is double integration method. Now we have to integrate one more time. Okay, now we have to integrate one more time. Now integrate integrate with respect to x again. What you will get? You will get EI. You call this as equation number 2. You call this as equation number 2. Okay. EI into what is integration of dy by dx? Integration of dy by dx will be y. That's it. Is equal to W by 4 is the constant. Integration of x square is what? X cube by 3 minus WL square by 16 x integration of constant plus again C2 integration constant C2. Call this as equation number 3. Okay, call this as equation number 3. Now we have to again find the value of constant C2. How to find the value of constant C2? Again by using boundary conditions. In earlier equation we had dy by dx, that is slope. Okay, slope as LHS, but in this particular equation we have deflection y as the LHS. Okay, now we have to apply boundary condition corresponding to deflection only. You have to apply boundary condition corresponding to deflection only, so that we will get the value of constant C2. Okay. Now when you take deflection at point A is 0 and it goes on increases along with the span of the beam. At center it will be more, again it goes on decreases, and again it will be 0 at support B. Therefore we will utilize the boundary condition at support A only at x equal to 0. Okay, at x equal to 0, what is deflection y? Y is also equal to 0. This boundary condition we will utilize so that we will get the value of C2. Okay, at boundary condition you write the sided line, boundary condition at x equal to 0, the deflection y is also equal to 0. Okay, at support there is no deflection is 0 and x equal to 0. Now substitute y equal to 0 and x equal to 0 in this equation 3. Therefore equation 3 becomes equation 3 becomes 0 is equal to, okay, 0 is equal to, here we have x term that becomes 0, minus here we have x that is also 0, plus C2. Therefore C2 value is also becomes equal to 0. Okay, by this we got the value of constant C2. Now substitute the value of C2 in this equation 3. You will get the final equation for deflection. Okay, substitute value above value in equation 2. Sorry, in equation 3. Therefore the equation for deflection EI into Y is equal to W by 4 Wx cube divided by 4 into 3 12 minus WL square by 16x plus 0. Okay, call this as equation number 4. Okay, call it as equation number 4. Now we want expression for deflection of the beam at the center. We want deflection at C. Correct? We want deflection at C. Okay. Now you need to utilize equation number 2 and equation number 4. Okay, for obtaining deflection and slope of the simply supported beam. Okay, now the double integration is completed. Okay, double integration is completed, means step 2 is completed. Next we will move on to the step 3. Step 3 is to find deflection, to find the expression for deflection of the beam. Okay, that is only the step 3. Step 1 is finding the reactions. Okay, finding the reactions and finding the moment at the section X and equating the standard moment equation to that of moment obtained. We will get one equation. Step 2 is doing double integration. Doing double integration means you have to initially integrate with respect to X Then you need to obtain the value of integration constant by applying boundary condition, substituting the value of integration constant in this equation. You will get one equation. After that, you need to integrate the same equation one more time, obtained equation one more time, that is integrate with respect to x. Again you will get one more integration constant. Again you need to apply boundary conditions, substituting the value of ct. You will get one more equation. Okay, so in this process, equation 2 is the equation for slope, finding the slope. Okay, this equation is used for finding the slope. Dy by dx means what? It is nothing but slope only. Equation 4, whatever we have obtained, it is the equation for deflection. If you want to find deflection at any point along the beam, okay, if you want to find deflection at any point along the beam, you have to utilize this equation number 4. Ei into y. Y is nothing but it is deflection. Now we will find deflection at the center of the beam. We will find deflection at the center of the beam, means at a distance L by 2 from the support. Okay, at a distance L by 2 from the support. Now you need to substitute x equal to L by 2 here, then you will get deflection at the center. Okay, therefore deflection at center, that is x is equal to L by 2. Okay, x is equal to L by 2. The equation 4 becomes you need to substitute x equal to L by 2 in this equation. You will get the deflection at C, means deflection at center. YC you will get. Therefore EI into YC. Okay, if you substitute x equal to L by 2, y becomes YC, deflection at C. It becomes deflection at C is equal to W by 12 into x cube is there. In place of x, you need to substitute L by 2 whole cube minus WL square by 16 into L by 2. Okay, on further simplification, it will be W by 12 L cube by 2 cube is 8, correct, minus WL square by 16 into L by 2. Okay, further simplification, WL cube by 12 into 8, 96, minus WL cube by 16 into 2, 32. Okay, so LHS will be 96 only here. I'll write one more step. If you take WL cube common, WL cube into 1 by 96 minus 1 by 32. Therefore WL cube into LCM is 96. Here 1, here 3, correct? 1 and 3. Then it becomes minus 2 WL cube by 96. 2 ones are 248. So it becomes, final equation becomes how much? Minus WL cube by 48. minus WL cube by 48. Okay, therefore deflection at C, EI into YC, EI into YC is equal to minus WL cube by 48. Therefore YC deflection at C is equal to minus WL cube by 48 EI. 48 EI 48 EI, and this minus indicates what this minus indicates? The deflection is in downward direction. Okay, deflection is in downward, that is the meaning. Or else you can write one more step, YC is equal to WL cube divided by 48 EI. In the bracket you can mention it as downward. In the bracket you can mention it as downward. Okay, so this is how we find equation for deflection at the center. Okay, you can also determine slope of the curve. Okay, you can also determine what is slope at support A here, dy by dx or theta A. Okay, how to find slope at support? Using the slope equation, dy by dx equation, this equation number 2, you can find the slope equation for the slope. Okay, you need to determine equation for slope as well for completion of this derivation. That is the last step, step 4. Step 4 slope. Okay, to find slope, in this slope equation, okay, in this slope equation, if you substitute x equal to 0, you will get what is the corresponding slope at the support, correct? If you substitute this x equal to 0, you will get what is the corresponding slope, that is dy by dx at the support. Substituting, we'll write slope at support. That is x equal to 0. Okay, so this equation becomes EI into dy by dx, EI into dy by dx, that is slope at x equal to 0 is equal to w square by 4, where x is 0, w into 0, this first term becomes 0, that is x equal to 0 in equation 2. Okay, 0 minus WL square by 16, it is a constant, minus WL square by 16. So EI into this dy by dx at x equal to 0, slope at x equal to 0, you can write it as theta A. Slope at A, correct? Slope at A, dy by dx at x equal to 0, instead of writing this in this way, I have just written as theta A. Slope at A is equal to minus WL square by 60. Therefore, slope at A, slope of the reflected shape of the beam at support A is minus WL square by 16 EI. So this is the final equation for slope. Okay, so this completes the derivation. Are you able to follow the things, students? Here, have you understood any doubts here? Any doubts you can ask? Any doubts? Any clarification needed, students? Any clarifications required? Anyone reply? Bharat?
No, sir.
Okay. See, the procedure is, it looks like a lengthier one, but the process or procedure is very simple. Okay. See, as we have done 2 times integration, as we have done double integration here, that is why it looks like a lengthier derivation. But procedure is very simple. Very simple. Okay. I'll just explain it once again briefly. See, we are finding equation for deflection and slope of a beam, simply supported beam carrying central concentrated load at the beam. Okay. Initially, what we have done, we have determined the support reactions that we got it as W by 2, and we have considered a section XX additional 6 coulomb support, and we found out moment at support, moment at the section X, we got it as W by 2 into X. Okay, and we know the standard equation for M moment, that is EI into d square y by dx square. So from these two equations, we got one more equation, that is EI into d square y by dx square is equal to Wx by 2. Okay, the next step is integration. This is the first step. Next step is doing the integration 2 times. Okay, along with finding the integration constants by applying boundary condition. Initially, I have integrated the equation with respect to x for the first time. We got this equation. So plus C1 is the integration constant that we have to obtain by applying boundary condition. Okay, here dy by dx is nothing but it is a slope. Okay, so using this slope, or by applying the boundary condition with respect to the slope of the beam, we can obtain the integration constant C1. Okay, at integration constant C1, we all know that at x equal to L by 2 at the center, slope is 0. It is horizontal. If you draw the tangent to the curve, it becomes horizontal. Slope is 0. That is dy by dx equal to 0. That is x equal to L by 2. At x equal to L by 2, dy by dx equal to 0. Okay. Now in the same equation, I have substituted dy by dx, that is slope equal to 0 and x equal to L by 2. I got the value of C1. After getting the value of C1, you need to substitute the same value in this equation 1. Finally, you got equation for slope of the equation. This is about first time integration. Then again you need to integrate this slope equation with respect to the x. You will get deflection. Then equation for the deflection, ei into y. Y is nothing but deflection. So you got one more integration constant C2 that also should be determined by applying boundary condition. Okay, by applying boundary condition. Here we know that the y represents deflection. Now we have to apply boundary condition corresponding to the deflection of the beam. We know that at the support the deflection is 0. There is no deflection. This yc becomes equal to 0. Okay, the same boundary condition I have applied here. At x equal to 0, y equal to 0. Okay, so this y equal to 0 and x equal to 0, if you substitute, C2 becomes also equal to 0. If you substitute the value of C2 in this equation 3, you will get one more equation, that is equation number 4, that will represent the deflection equation. Equation 2 represents slope equation, equation 4 represents deflection equation. Okay, now we are interested to find the value of yc, deflection at the center. So we already obtained the equation for this deflection. Here we have the deflection. If you just substitute x equal to L by 2, okay, x equal to L by 2 in this deflection equation, you will get deflection at the center. You need to do some simplification. After final simplification, you got deflection at C as WL cube by 48 EI. Similarly, if you want to find slope at, there is some slope at support A and support B, correct? Therefore, if you want to find some slope, if you want to find the slope at support A, you need to utilize slope equation. This equation number 2. You need to substitute x equal to 0 If you substitute x equal to 0, you will get slope at a, that is theta a, you will get it. Okay, same thing I have done here. A into dy by dx, that is slope at x equal to 0 is equal to 0 minus x equal to 0 only here. X equal to 0 only. This becomes 0 minus WL square by 16. Minus WL square by 16. After simplification, finally, I got the value of slope, that is theta a is equal to minus WL square by 16 AI. Okay. So this is about the deflection and slope of a beam, simply supported beam subjected to concentrated load at the center of the span. Okay. Now we will solve a simple problem on the same kind of a beam. Okay, we'll solve a simple problem on the same kind of a beam. I'll have to write that problem first. Write the problem. Problem number 1. You write it. A beam 6 meter long, simply supported at its ends, is carrying a point load of 50 kilonewton, at its center. Okay, full point. The moment of inertia the moment of inertia of the beam is given as equal to 78 into 10 power 6 mm raised to 4. Full point. If E, that is Young's modulus, if E for the material of the beam is equal to 2.1 into 10 power 5 Young's modulus Newton per mm square. Calculate first question in that. Deflection at the center of the beam. Deflection at the center of the beam. Second question is slope at the supports. Slope at the supports. Okay, it's a direct question. Everything is given. You need to just substitute the relevant values in the relevant equation. You will get the required deflection and slope at the supports. Solution. First, you read all the given data. Okay, all of you write the given data. Everything is given. Length of the beam is given. Then load acting is given as 50 kilonewton at the center. W is given. then moment of inertia I is given, Young's modulus E is given. Okay, everything, every given data you write first. A beam 6 meter long, L is equal to 6 meter, simply supported at its ends, carrying a point load W is equal to 50 kilonewton. In terms of Newton, it will be 50 into 10 power 3 Newton. The moment of inertia of the beam is equal to I is equal to 78 into 10 power 4 mm4, and Young's modulus E is 2.1 into 10 power 5 Newton per mm square. You need to calculate deflection YC, deflection at the support, and theta A. Correct? Deflection at the center and slope at the support. Just substitute, write that equation for YC and theta A. YC is WL cube by 48 EI, theta A is equal to WL square by 16 EI. Just utilize those equations, just make a substitution, you will get the answer. Calculate and tell me the answer, any one of you. You just make substitution, you write, you copy those formula and you make the substitution, you will get the answers. What is the formula for deflection at the support? Sorry, at the midspan, YC is equal to WLQ by 48 EI. Just take that equation. YC is equal to WL cube divided by 48 EI. Okay. Therefore, YC is equal to W is 50 into 10 power 3. Length L is 6 meter. So this Young's modulus, it is in terms of Newton per mm square. So we have to maintain a single unit. The 6 meter is there now. I will convert it into mm. So it becomes 6000 mm. It becomes 6000 mm. Okay. So 6000 cube divided by 48 into E is 2.1 into 10 power 5 into I, Young's moment of inertia is 78 into 10 power 4. 78 into 10 power 4. Therefore, deflection at the center of the beam is equal to, just calculate and tell me the answer. You just calculate and you will get the what is the deflection that may occur at the center of the beam. In terms of mm, you will get the answer. This is the first question. Okay, first question. What is that first question? Deflection at the center of the beam. Deflection at the center of the beam. Okay, well, if you check the answer, you have to get it as 13.73 mm. You have to get it as 13.73 mm. Similarly, what is the second question? Second question is slope at the supports. Correct? Slope at the supports. Slope at the supports. We have the formula. Correct? We have the formula. That is theta A or else theta B. Okay, you will get the same slope at both the sides. Okay, just substitute. It will be minus WL square by 16 EI. Okay, so this negative sign indicates the anti-clockwise rotation or anti-clockwise angle or anti-clockwise rotation of the beam, anti-clockwise deflection of the beam. So I will write as WL square by 16 EI. W is 50 into substitute 50 into 10 power 3 into 6000 square divided by 16 into E is Young's modulus is 2.1 into 10 power 5 into I 78 into 10 power 6. If you calculate the final answer, you will get theta A and theta B as 6.868 into 10 power minus 3 radians as answer. If you want to put the answer in terms of degree, you need to multiply by 180 by pi. Correct? Theta A is equal to theta B is equal to 6.868 into 10 power minus 3 into 180 by pi. If you multiply, you will get the answer in terms of degree. So if you calculate, you will get 0.39 degrees. Okay, it's a very simple problem. I hope you all understood. Okay, so to this we'll end the class and we'll continue in the next class.